Hello, you're welcome back. All right, so we'll continue from where we stopped. Now, in this video, we are going to be looking at the determination of coefficient of static friction, okay, in two surfaces. All right, the very first surface we are going to consider is a horizontal plane, okay, a plane that is horizontal. Now, of course, you know that static friction, okay, is a friction that keeps the body at rest, okay. It's a friction that actually keeps the body, opposes the motion of the body, but is strong enough to keep that body at rest. So that means in a static friction, we should believe that there is no movement, okay? That simply means that the net force that's supposed to produce movement on that particular object is equal to 0. So for us to actually determine the coefficient of static friction in a horizontal plane, this is the setup I have here on the screen, okay? I have a mass that is on the surface. This is the mass that is actually that's supposed to move, and this is the mass that is being affected by friction due to its movement or motion over the surface, right? Now, this mass is actually connected via a frictionless pillow to another mass M2. Now, what is the idea of M2? M2 is meant to pull on this mass, okay, so that it actually moves. But it happens that because we are dealing with static friction, mass M1, okay, it's set to be at equilibrium. It's not moving, all right? So now I want to determine the coefficient of static friction. How do we do that? We know very well that this mass is actually is creating a tension. Mass M2 is creating a tension, okay, that is meant to pull M1. And you know very well that frictional force actually will exist on this surface. And I told you that frictional force is always opposite the motion. So if the motion is actually forward, then the frictional force will actually be acting backward. All right, so let me call that F. So now, because of the fact, okay, that this body M1 is at equilibrium, okay, for an object to be at equilibrium, remember the net force on that object is 0. And how do you get the net force? The net force for two forces acting in opposite direction is going to be their difference. So I have to subtract the two forces. So the net force on mass M1 is going to be equal to the difference, tension minus the frictional force F, okay, and we know that that is equal to 0. Okay, tension is the weight. What is actually bringing about the tension is the weight of the mass M2. So tension is going to be the weight of M2, that's M2G. And we already know that frictional force, I can take frictional force to the other side of the equation, okay, it becomes plus frictional force. And frictional force already we know is mu normal reaction, okay. I call this symbol the symbol mu, which of course is the coefficient of frictional force, okay. Now the question is, what's the normal reaction? We've talked about this, okay, when we treated Newton law of motion, so that action and of course reaction is always equal, okay, and opposite. So normal reaction definitely will be, remember weight is actually acting downward, weight is M1G, okay, and of course normal reaction is acting upward, and they are equal and opposite. So invariably now the normal reaction of this surface now is going to be equal to the weight of the body that is actually placed on it. So we can now go further now to get, okay, so our formula now is going to be equal to M2G, then multiplied by the coefficient, then times the normal reaction, which of course is M1G, okay. So now I can now get my coefficient. What's my coefficient? My coefficient is going to be equal to, of course, M2G divided by M1G. You know what happened? G cancels G, okay. So in a horizontal plane, the coefficient of static frictional force is given as M2, the mass of the object, that's the mass of the pulling object, okay, the M1, the mass of the object that is on the force all over M1, okay, the mass of the object that is on that surface, M2 all over M1. So please take note of that. All right, so now we're going to go to the second, another type of plane, which of course is an inclined plane. Remember, a horizontal plane is horizontal, but we have another plane known as an inclined plane, okay. So an inclined plane is a plane that is actually inclined at an angle. Okay, so let me just do this. the plane is inclined triangle. So invariably now what we do is that we place a weight on the inclined plane. Okay, place a weight on the inclined plane. Now let the mass of the weight be m. Okay, now without even applying any force on this okay, on the weight or pushing the weight because of the inclination of the plane. Okay, let's say the inclined plane is inclined triangle of theta. Okay, depending on how inclined this plane is, there is this tendency that this weight will just want to slide down on its own. Okay, so this is the direction of the motion of the weight. All right, but of course you know very well that if you're gonna slide downward, then the frictional force will be acting upward. So frictional force F will be acting upward. So the question is, okay, so what is this force that is actually pulling this? Because there's no, we didn't, nobody's actually touching this mass to come down. It just come down on its own due to the inclination of the plane. So what is this force here that is actually pulling, that's horizontal to this plane, that is going to pull this weight downward? Okay, that force is actually a force that is horizontal to the plane, and that force is given as mg sin theta. Okay, I don't want to go through the process of proving any formula. I can do that later. Okay, so know that the force that is horizontal to an inclined plane is giving us the mass mg, or the weight of the object here, then sin theta. Okay, it's a component. It's of course a component of the mass, which is the vertical component. But that's just take it. All right, just I want to establish a formula. Okay, later I can actually go to the derivation. I just want to establish formula. So we simply mean that it is this mg sin theta that is meant to, that is meant to drive this mass downward, and the frictional force, okay, is opposite to that particular force. Okay, and therefore for the fact that we are studying static frictional force, okay, we should actually note that this particular mass is at equilibrium. It's at rest, it's not moving. Okay, so that simply means that net force now, net force, which of course is going to be equal to the force that is actually pulling the mass downward, which is mg sin theta, then minus the frictional force, okay, should actually be equal to 0. Why? Because the net force is 0. Okay, so now we can now get our coefficient. So I'm having mg sin theta. Then of course you know very well that frictional force is mu normal reaction equal to 0. So this is going to be mg sin theta. Okay, now the question is, how do we actually evaluate normal reaction of a plane that is inclined, owing to the fact that it is not horizontal? Okay, to get the normal reaction of a plane that is inclined, okay, is we actually multiply cos theta to the weight of that object, because it's always giving us mg cos theta. This is for the weight that is inclined, so the normal reaction is always giving us mg cos theta. So please take note of that. Okay, not mg in the case of horizontal plane, but mg cos theta. All right, so now this is going to be equal to 0. Okay, so rearranging this equation, remember I'm looking for this, so I take mu mg cos theta to the right side of the equation. It becomes, of course, I will have mu mg cos theta, right? Of course, it was plus there, so as it goes over to the right side of the equation, it was minus, please pardon me. It was minus here, so I take it to the other side, it becomes plus, right? So of course I'm gonna have is equal to all right. So now from here, now I can get my coefficient, which of course is mg sine theta. Then I divide it by the whole of this, mg cos theta. So mg cancels mg. So that you now have that coefficient now is going to be equal to tan theta. Alright. Sin theta all over cos theta is tan theta. So for an inclined plane, the coefficient of frictional force or the coefficient of static frictional force is just given by tangent of the angle of inclination. Okay, of course you know that the theta there, the theta is the angle of inclination of the plane, angle of inclination. All right, so these are basically the things you ought to know. Okay, so I think I could actually solve question. I can solve question. All right, please pardon me. So let's get some question and see if we could do justice to them. So I will go right to frictional force. Okay, so here I have a question. It goes this way. Do I have any question before that? Okay. All right, so here we go. I'll solve this one, then we'll now look at another. It goes this way. Example 1. If an object must begin to slide on a surface inclined at 30 degrees to the horizontal, the coefficient of friction is, okay, so the coefficient of friction is easy. So the angle of inclination is 30 degrees according to the question. So the coefficient of friction, of course, is going to be tan 30. So using tan 30 here, I use special angle to find tan 30. All right, special angle triangle. Of course, you know, in special angle triangle, the hypotenuse is √3. Okay, this is 60 degrees, this is 30. The opposite to the 30, okay, is 1, and the opposite to 60 is 2. And of course, you know that tan is always giving us, okay, tan theta, or in this case, tan 30. Tan is always given as opposite all of adjacent. The opposite of 30 is 1. Okay. And of course, the adjacent of 30 is 2. All right. Opposite of 30 is 1. Adjacent of 30 is 2. So that simply means that the coefficient of frictional force there is 1/2, which is 0.5. Okay, so that's how we actually evaluate that. Now let's talk about dynamic friction. Everything I have actually discussed so far is static friction, okay, when the frictional force keeps the body in equilibrium. Now we're going to talk about dynamic or kinetic friction, okay. Now it should be noted that, okay, for kinetic friction, that object is not at rest, it started moving, but the friction is there to oppose the motion, right? So invariably, the same setup we're going to be we actually considered previously, which of course is horizontal plane. Okay, so we'll consider kinetic friction in a horizontal plane and of course in an inclined plane. Okay, so I don't need to draw the diagram again. I will just use the formula I used before. Okay, remember the formula I used before, that for the one of the body being at rest, so that the net force, which of course is the tension, minus the frictional force, is equal to 0. But in this case, the net force is not equal to 0. Okay, the net force is actually producing mass times acceleration. Remember, most force is mass times acceleration, right? So which simply means that that body is actually moving. The system is moving. Both mass m1 and m2 is moving. Okay, so that will be their mass times acceleration. So of course, what is the tension? Remember, the tension is m2g, the weight of the second mass. Okay, and of course, you know that our force is mu normal reaction. Okay, and the normal reaction, you know that that's the weight of the object on the surface. Okay, is equal to the acceleration, mass times acceleration. Remember, it's not only one mass that is accelerating. As m2 is moving, m1 is moving. So I'll have to write two of them. That's going to be m1 plus m2. Then of course multiply by the acceleration. So with this formula now, you can be able to get the acceleration of the system that is actually under the influence of kinetic friction. Okay, so please take note of this formula. So this is what we use when we discover that that system is actually in motion. Okay, so I will apply this formula in the next video. See you in the next video. Thank you very much.